Watch this. In the time it takes to finish this sentence, a flat 2D image expands into a fully realized 3D wireframe. Traditionally, getting to this result required an immense computational tax. You either spent days manually sculpting the asset, or you relied on per-scene optimization techniques, like standard neural radiance fields, which trap the GPU in thousands of iterative training steps for a single object. InstantMesh bypasses that entire process. It is a feed-forward framework that generates a high-quality 3D mesh in under 10 seconds, completely stripping out the need for per-scene optimization. When generation drops from hours to seconds, the entire production pipeline shifts. AAA game studios can populate fast environments dynamically, spatial computing interfaces can generate assets on the fly, and robotic simulation environments can instantly spawn varied training terrains. Shifting from per-scene optimization to a feed-forward architecture addresses the primary throughput limit for generating complex, large-scale spatial environments. The InstantMesh pipeline begins with the hardest starting point possible, a single flat 2D image. Reconstructing a full 3D object from one angle is an ill-posed mathematical problem. From the perspective of a single camera lens, there are innumerable geometric configurations that could perfectly match the visible silhouette while hiding complete chaos in the shadows. To solve this, the framework relies on its first major component, an off-the-shelf multi-view diffusion model. Think of this model as a police sketch artist. By drawing on a massive semantic prior, a deep pre-trained understanding of structural anatomy and common object shapes, it makes highly accurate logical deductions about the angles we cannot see. The model hallucinates unseen angles by progressively demoising data, conditioning the output on the original 2D image. It locks precise geometric anchor points across the grid, ensuring all four generated perspectives belong to the same physical object. At this stage, the multi-view diffusion model hasn't actually created 3D space. It has simply generated a consistent multi-angle 2D blueprint for the next neural network to interpret. Curious analytical tone. This poses the next major mathematical challenge. How exactly does a neural network translate a handful of flat images into continuous 3D space? This is the job of the framework's second pillar, the Sparse View Large Reconstruction Model, or LRM. The mechanism works like a medical CT scan, where a dense internal 3D volume is mathematically reconstructed from just a few flat 2D X-ray slices. In this context, we're operating with incredibly sparse views, often just 4 to 6 images. The system accepts this extremely low input count to keep memory limits in check, managing a tight computational trade-off while fighting to maintain geometric accuracy. The LRM uses transformer cross-attention, breaking 2D images into individual tokens and establishing mathematical links to a floating 3D volume. To save resources, this volume collapses into intersecting orthogonal planes, efficiently projecting spatial data onto flat X, Y, and Z axes. The LRM's transformer architecture is the spatial engine here. It instantly converts scattered 2D blueprints into a highly structured 3D coordinate map, completely bypassing the need for iterative, per-scene training. But there is still one final bottleneck. Translating this spatial map into a hard 3D mesh is traditionally done with volumetric rendering, a process far too slow for a 10-second pipeline. Volumetric rendering is like trying to sculpt fog. The network has to fire thousands of computationally expensive ray samples into a density volume just to estimate where a solid surface might eventually begin. InstantMesh breaks this final speed limit by deploying a differentiable isosurface extraction module. Think of this like industrial vacuum forming. The module drops a flexible grid, snapping tightly over data points to instantly define a hard outer shell. This extraction is differentiable, allowing error gradients to flow backward from the mesh surface through the network to refine weights. This explicit surface allows direct geometric supervision using depth maps, dictating surface distance, and normal maps, specifying exact X, Y, and Z facing directions. By directly optimizing these explicit properties rather than guessing through implicit fog, InstantMesh shatters the standard optimization bottleneck, crossing the finish line in just 10 seconds. Achieving this speed requires massive upfront training. The framework is trained on highly curated public 3D datasets, utilizing vast repositories of synthetic multi-view images, perfectly paired with their ground truth depth maps. This chart shows the raw compute hours required by traditional score distillation sampling optimization models compared directly to the minimal inference time of InstantMesh. The feed-forward approach effectively flatlines the generation latency. The architecture does have limits. InstantMesh occasionally struggles to resolve extremely high-frequency microdetails, delicate thin structures, or complex multi-object scenes that are underrepresented in its current training data. To accelerate solutions to these edge cases, the researchers released the entire codebase and weights as open source, handing the tools directly to the AI community. While a feed-forward pipeline occasionally drops a micro-detail that an hours-long optimization catches, it unequivocally wins the macro-level race for scalable pipeline integration. In 30 seconds, 1. The diffusion model analyzes a 2D image, hallucinating unseen angles. 2. The sparse view LRM translates these tokens into a structured 3D triplane. 3. The ISO surface extractor optimizes the explicit mesh, dropping generation time to 10 seconds. InstantMesh demonstrates that the combination of diffusion priors and differentiable geometry provides a template for integrating high-quality 3D generation into real-time applications. If you want to stay at the edge of spatial computing and AI architectures, drop a like, subscribe, and come back to the Gradient Daily for more technical breakdowns.